Hello, hello. Oh, yeah. Oh, no, I just Yes, that was wrong. So. I never just wanted one. No. We're in this. Yeah, I was looking at the final.
They did. So. All right, it's 1 o'clock, so let's go ahead and get started. Good afternoon, everyone. How's everyone doing today? Good. Made it to the second week. Made it past the first week of class, so we are rolling this semester. Okay, so you probably have noticed on what day was it? I think it was Friday. I posted the first homework assignment, and so that homework assignment stuff is going to be due a week from today, right? So typically for the homework assignments, you have two options, and so you can, all the homeworks most of the homeworks that we're doing in this class are going to involve, calculations with pencil and paper, and so if you finish those before the lecture, you can turn it in the lecture, and then I'll grade and give back to you, or you can scan your homeworks and then just upload a PDF onto Canvas, right? And so a lot of people tend to do that one because I set my homework due dates to be 11:59 p.m. on the day that it's due. And so if you want to turn it online, you have maybe half the day more to turn it. Okay. And I do that just because I realistically I can't get to grading stuff the day that it's turned in. So I give you up until literally the last minute of the day for you to turn it in for that. Okay. And so the subject of that homework, part of it is drawing cash flow diagrams, and so you should be able to do the first problem on it, but everything else that you need for the homework we're going to learn this week. Okay, so that's all my announcements, and so are there any questions I can answer before we get started today? Okay, all right, so let's go ahead and pick up where we left off. And so last week we kind of left the lecture with kind of a hypothetical situation, right? And that hypothetical situation was based around this idea that the value of money changes with time, right? So let's go ahead and pick up right where we left off. And then talk about the time value of money, okay? All right, and so if you remember from last Thursday, the theoretical situation I left you with is that, you can have two options. And so you can either have $100 right now, or you can have that $100 a year from now. So it's the exact same $100 bill. It's just that, in the one case I gave it to you right now, the next case I put it in a vault somewhere, and then, I give it to you a year from now. Okay? And the question at the time was which was better? Okay. And what we talked about was that the most preferable option here is to have the $100 today, right? And there's a lot of reasons for that. And so if you have $100 today, first of all, if you really want, you can take that $100 bill and put it in your pocket for a year and have option 2, right? Or what most people tend to do is that they take that $100, they either spend it on something, and so they use that to buy food, rent, whatever, or you can take that money and you can invest it and grow that money over time. Okay. Okay. And what we're going to be focusing on a lot over the next few weeks is the second one, right? And so it's the idea that if you take money and you invest it, we're going to learn exactly how money grows with time in terms of interest rates. Okay. And I think, this information kind of comes at a very timely time, in the world, because, I think a lot more people nowadays are getting into investments. Like I said last time, a lot of people are getting into stocks, crypto. A lot of people are being more, more creative with their money. And so having some knowledge about this, you may already know a lot about this information already, but having some knowledge about this is kind of good for where we're going. Okay. And this is especially good, because after you guys graduate, a lot of times you're going to work for a company where they're going to have options like this as part of your compensation package, right? And so they might give you options for like a 401k, a retirement fund. They might give you options for you to buy stocks in the company, right? And so kind of understanding these things is just kind of good, just life skills in general. And surprisingly, I learned a lot of this, through, I was fortunate enough, my dad taught me a lot of these things when I was growing up. But as I was talking to a lot of my friends, especially now that, a lot of my friends are getting into their, late 20s, early 30s, a lot of my friends actually are not as aware of these things as, as I would have thought. So, it's great that, we can learn this in the class here so that you at least have some of that basic understanding. Okay. But the important thing is that, the important takeaway I want you guys to know is that money's value doesn't stay stagnant over time. And so, depending on what you do with the money, its value is going to change. Okay. Okay. And of course, this is relevant when you're talking about things like um, like an investment account, something that you're going to leave the money alone for a while, right? But this is especially relevant for specifically engineering projects because, just the nature of engineering projects, they're not completed overnight. They're not completed in a week's time. A lot of engineering projects take a very long time for them to complete and mature. Right? Okay. And so I'll give you an example. You may have read it in the news somewhere, but our college here, or the ECS college here, Cal State Fullerton, we're planning to renovate a lot of the buildings and the lab spaces that we have here, right? The unfortunate thing, about running in the news right now, especially for you guys to read it, is that you guys unfortunately won't get to benefit from it at all because you will be long gone before any of this happens. I might be long gone before any of it finishes. But if you're planning a long-term engineering project like this, you need to take that into account. So as you secure funding over time, you need to take into account the fact that the money's value that you're using, that's going to change with time as well. Okay, and that can be a very tricky thing if you don't really know what you're doing. Okay. Any questions on this so far? Okay. All right, so let's talk let's start at kind of the basics. Let's talk about interest and interest rates. Okay. Okay. All right, and so interest rates, the idea behind interest rates is that money is a very, very powerful asset. In particular, cash is a very powerful asset, right? It's so valuable that often people are willing to pay more money over time in order to have, money immediately right now. Okay. Okay. And so if you've ever borrowed money for a loan or, borrowed money from a friend, you're very familiar with this concept. And so, the idea with the loan is that you take out money so that you can have it right now to pay for something, but over time you pay that money back plus the interest on top of it. So what you end up paying back numerically is more than kind of what you received at the beginning. Okay. And that additional money that you use to pay back the loan on top of the original amount, we call that the interest. Okay. Okay. And so usually the way that we express interest, but usually the way that we compute it is based on a percentage of the original amount. I guess maybe I should put a definition here first. So the original amount that you use to to take out a loan, we often call that the principal. Okay. And then the interest payments that you make, or the additional money that you're paying to use that principal, we call that the interest, right? And that interest is usually based on a percentage of the principal. Okay. Okay. All right, so as a very quick example, let's do an example with simple interest. Okay. And so let's say that your friend comes to you and he said he wants to start a business, but in order to start his business, he needs an extra $5,000 in cash right now. Okay. Okay. Right. And so you agree to pay him, and so you agree to give him that money, and so you write a check for $5,000. And so what your friend tells you is that, I expect my business to take about 5 years, in order for us to be really profitable. And so what I'm going to do after 5 years is I'm going to give you back that $5,000 after 5 years, plus interest. And the interest that he's going to give you back is at a rate of 8% of the principal per year. Okay. Right. And so in this simple problem, what we want to compute is after those 5 years, how much money is your friend going to pay you? Okay. All right, so this is a problem with simple interest, right? And so what simple interest means is that, you know, the amount of interest payments that we are going to compute is only based on the original principal amount. Okay. And so in this case, the original principal was the amount that you lent to your friend, which is $5,000. Okay. And so the way to think about this problem is that, you know, for each year that your friend is using your money, he's going to give you 8% of that original $5,000, right? And so let's compute 8% of 5,000. Okay. Okay. And so to compute 8% of that, we have our original amount, which is $5,000. Okay. And then we're going to take 8% of this. And so 8% of $5,000 is just, we're going to multiply by 0.08. Okay. Right, so you can punch this into a calculator, you do 5,000 times 0.08, and what you get is $400. Okay. And so your friend is going to pay you $400 per year to use your money. Okay. So that's the fee, that's basically the fee that you're charging your friend in order to use your money. Okay. And so if that's the price per year, you know, you're lending your friend money for 5 years. So let's go ahead and multiply this by 5. Okay. And so you do $400 times 5, and $400 times 5 is $2,000. And so that's the amount of money that your friend is going to owe you just from the interest. Okay. Okay. And so after the 5 years, your friend is going to pay you the $2,000 interest. Okay. Plus the original amount that he borrowed from you, right? And so he borrowed $5,000, and so he's going to pay you $2,000 plus the $5,000 principal. Right, and so to get the total payment, we just have to add those two up, right? So total payment. Okay, this is equal to $5,000. This right here was our principal plus the $2,000. Okay, this was the interest. Okay. And so in total, you know, at the end of 5 years, you're going to get a check of $7,000 from your friends. Okay. Okay. Any questions on this example here? Yeah.
If he pays you back in 4.5, that last year we did $100. Or
Yeah, and so, yeah, so if you're paying back for a half period, then you would only pay for half that. All right, and so this example here illustrated the idea of simple interest. And so, I think I mentioned up here, but in simple interest, the amount of interest payments that you compute is only based on the original principal. Okay. Okay. And so what we can do is we can take this formula up here, this 5,000 times 0.08, and then turn it into kind of a generic form, right? And so the generic formula for simple interest right? This formula is P times I times N. Where P here, this is the original principal. Okay. I here is the interest rate. And N here, that's the number of time periods that the interest is accumulating. Okay. Okay. And so it's a very simple formula. So you just take those three things and multiply each other. The only thing you have to be careful of here, and you have to be careful of this, for all of these type of calculations, is that when you plug in the interest rate, you have to plug it in as a decimal, not as a percentage. Okay. So let me write this in red because that's very important. Okay. And so like in the previous problem, we had an 8% interest rate. And so if you plug in 8 for I right there, your friend is going to think that you're scamming him because he's going to owe you like $20,000, which is going to be $200,000. And so, you have a nice friend and he makes it big, maybe you charge him that much, but usually the interest rates are expressed as decimals. Okay. Okay. And so simple interest calculations are, they're very straightforward. That's why we call them simple interest. The unfortunate thing is that most loans in reality, in most cases like this, they're not simple interest. And so simple interest, I think it's a nice concept just for introducing the idea of interest payments, but reality doesn't really work like this. And so in reality, most loans and most places that you borrow money from, they use a concept called compound interest. Okay. Okay. And so the biggest difference between simple interest and compound interest is the fact that the principal is actually going to grow with time. And so with simple interest, you can have that formula be for any number of periods, right? You can have that up to 10 years, but this P here is always the same in in simple interest. Okay. So that never changes. But for compound interest, the way it works is that whenever you accumulate interest, then that interest fee gets rolled into the principal. Okay. And so since the principal amount is changing, each time, right? And so in this, in this particular example, we're doing a simple loan, right? And so for each year that the loan is out there, then the principal is getting bigger, because what's happening is that, the lender, which is you in this case, you're charging interest to use that money, and then that extra money that you're charging them gets rolled into the principal, right? And so now, the next time period or the next year, the amount of interest is going to increase because, your principal is going to increase, okay? And so for loans, of course, this is something that benefits the lender, because then, they can charge you more money to use the money. But if you're talking about kind of a long-term loan where you kind of pay this off into multiple payments, this actually helps the person actually borrowing the money. And we'll talk about that when we get to recurring payments later today. Okay. And so just to kind of illustrate this idea, I think it's best to kind of, view it through an example. And so let's do the same example we did before, but instead of simple interest, we're going to do compound interest. Okay. And so just as a reminder, your friend, you are loaning your friend, so your friend is asking for $5,000. Okay. From which he's going to pay you back at 8% interest per year, but instead of simple interest, it's now going to be compound interest. Okay. All right. And so, this is going to be quite a few numbers. And so I'm going to go ahead and organize this into a table. Okay. And so let's go ahead and make a table, right? So let's say we have a column for the year. Right. Since the principal amount is going to change each year, we're going to have a column for that as well. Okay. Okay. We're going to have a column on the interest. Okay. And since the principal amount is changing, right, whatever interest that we accumulate is going to be rolled into the principal. Each year, we're going to have a new principal amount as well. Okay. Okay. All right. So let's start in year one. And so in year one, the principal amount is just the amount that that you lent your friend, right? And so the principal here is going to be $5,000. Okay, so that's where the loan is starting out. And if we compute the interest on this year, and so the interest is going to be whatever the principal is, which is $5,000. Okay. We're going to multiply by the interest rate, which is 8%. Okay. And just like we saw above, and so the interest for that year is going to be $400. Okay. Right. And so this is kind of where we stopped for the simple interest problem. So for the simple interest, all we did was we took this $400 and just multiplied it by 5, and that was the total interest, right? But now we're doing compound interest. And so for compound interest, what we're saying is that at the end of the first year, we're going to have our original principal, which is $5,000, plus the interest for that year, okay, which is $400. And so our new principal at the end of the year is just going to be the sum of these two, okay? And so it's going to be $5,400, right, at the end of year one. And so when we move on to the next year for year two, then the starting principal for that year is whatever the principal was at the end of the previous year. So it's going to be $5,400. Okay. Next, let's compute the interest for year two. Okay. Right. And so for year two, just like before, we're going to take 8% of whatever the principal is. But instead of $5,000, our principal is now $5,400, right? And so we're going to take 5,400 and we multiply by 0.08. We get $432, okay? And so we can see the interest is growing, right? And so it started at 400, now it's 432 for this year. All right, so let's go ahead and compute the new principal. And so the new principal is going to be 5,400 plus 432. And so we add those together, we get 5,832. And then for year 3, you know, we're just going to repeat that process. And so at the end of year 2, we ended up with a principal of 5,832. And so we're going to go ahead and move that to the next line. Okay. And then we're just going to repeat this process. And so I'm going to go ahead and fill it in, you know, fairly quickly. You know, I think, you know, only the first couple lines need to be narrated. You know, but you can kind of see the pattern going on here. Okay. Okay, and so if we follow that calculation all the way to the end, what we end up with is an amount of $7,347. And so under compound interest, you know, at the end of the 5 years, your friend is going to pay you this amount. Okay. All right. Any questions on this example here? Okay. All right, and so let's get a formula for compound interest, because you know, you can certainly make a table like this for any kinds of these problems, but you know, you can see it can get a bit tedious. And so the lucky thing is that we can sum it up in a very simple formula, right? Not quite as simple as simple interest, but still quite simple. Okay. And so the way the compound interest formula, you know, this formula actually has quite a few names, but for now we'll call it the compound interest formula. So our compound interest formula is going to be F is equal to P times 1 plus I. And we're going to raise that 1 plus I to the n power. Okay. And so let me go ahead and label these terms here. And so first we have P. And so just like before, P here is our principal amount. Oftentimes what we'll call P here, and the reason we give it the symbol P, is this represents a present sum of money, or you know, money that you have in the present day. Okay. And so I'll be using that you know, that terminology quite a bit. Okay. All right. So next we have I. And so I, just like before, is our interest rate. And just like before, this interest rate is going to be expressed as a decimal, right? So don't express it as a percentage. This n right here, this is the number of time periods. And so the in the previous example, we did an example with years, right? And so n here represents the number of years. But you'll also come over situations where you'll see the interest compounds every month. There might be situations where it compounds every week as well, but those are pretty rare. Okay. And so usually n here will represent either the number of months or the number of years, right? Depending on the problem. And so whether n, I get this question a lot. And so whether n represents, years or months, you kind of have to read, that's kind of something you have to read in the fine print. And so, for this class, it'll say most of the time in the problem whether the interest is compounding monthly or yearly. And so that's something to look out for this class. But out in the real world, that's something that you have to kind of read the fine print about, just to kind of make sure that you understand what's going on. Okay. And what's F right here? And so F here, if we're talking strictly about loans, this is the amount that you would pay back at the end of the loan period. Okay. But the term that we're going to use for this class is we call this the equivalent future sum, or future sum for short. Okay. And so based on this equation, what we're saying is that, if you have a principal amount, if you have a present sum of money today, with this interest rate, I, and the number of periods n, we can compute, basically how much that amount of money is worth in the future. Okay. And that's what this formula expresses. It's an equation of equivalence. All right, any questions on this? Okay. All right, so let's talk about equivalence a bit more, because that's an important concept for this class. Okay. All right, so the idea of equivalence is that when you're comparing amount of money, it matters how much time elapses in between those two. Okay. Another way to put this is that in order to kind of fairly compare amounts of money, okay. And so in order to accurately compare amounts of money occurring at different points in time, then you have to account for the fact that the money's value is going to change due to interest rates. Okay. Okay. And so kind of a simpler way to say this is that, if you want to compare, how much money that you have now compared to, the amount of money that you might have in the future, you have to take the interest rates into account. Okay? Hang on, I see a question in the chat, but let me finish writing this stuff first. Question in the chat. So professor, in the formula, what does the I stand for? The I stands for the, oh, you're talking about this one. So this is just the number one. And so it's not an I, it's just a number one. Yeah. Yep. Actually, that's a good point. So I forgot to do. And so, let's use the previous example and let's use the compound interest formula so you can see, first of all, how to use this formula, but second of all, the concept of equivalence. Okay. Okay, so in our previous example, we had a principal amount of $5,000. Okay. The I here was 8%, and so in terms of a decimal, this is 0.08. And our N here is 5. Okay. Okay, so let's go ahead and plug this into the compound interest formula and compute the future equivalent amount. All right, so we have F is equal to P, which is 5,000. Okay. Okay. Then we have the number 1 plus the interest rate, which is plus 0.08, raised to the 5th power. Okay. All right, so we go ahead and simplify this a bit. We have 5,000 times 1.08 raised to the 5th power. Okay. So at this point, you can punch this into your calculator, and what you get is 7,347. If you check back with our previous example with the table, this is exactly the amount that we got. Okay, and so this shows that this formula here, has the same, gives you the same information, but with a lot less. So let's tie this example here into this concept of equivalence. Okay. And so, for this example, we have basically two sums of money, right? And so we have the $5,000, right? So that's the original amount that you owed loaned your friend. Okay. And then we have the $7,347, which is the amount that he's going to pay you back after this 5 years. Okay? And so let's go ahead and label these two amounts of money based on when they're relevant in terms of time, right? So this $5,000, this is $5,000 that you have today, right? Because this is the amount that you're gonna lend your friend today in order for him to start his business. All right, and so you compare that to the $7,347. Your friend doesn't have this money yet, but that is money that he hopefully will have for you in 5 years. Okay. Okay. And so one way that we can say this, based on the interest rates, okay? And so based on an 8% interest rate, $5,000 today is equivalent to $7,347 5 years from now. Okay. And so one way that you can think about it is that, the $5,000 that you have today, its equivalent value is going to be $7,347 in 5 years. Okay. So this concept of equivalence, this is a little bit of an aside, but if you're interested in investing money in like stocks or crypto, this is something that you should be very familiar with. So usually for those kinds of mediums, you're going to take money that you have today and invest it in the market, right? The idea is that one day, maybe maybe a year from now, maybe 3 years from now, 5 years from now, you're going to take that money and withdraw it from the market. And what you hope is that the money that you put in is going to grow at a steady rate, at a steady interest rate over time. Okay. And so, if you're expecting, say, an 8% interest growth on your investment, then 5 years from now, your $5,000 should be worth $7,347. Okay. And that's kind of the hope with investing. Okay. Any questions on this? All right, and so let's go ahead and push on, right? And so another way that I like to think of this formula, so let me go ahead and write the compound interest formula again. Okay. Another way that you can think of this formula is that you can think of this formula as a conversion between amounts of money at two different points in time. Okay. Okay. Right. And so I use the word conversion, and as we start to introduce different types of cash flows, and so as we introduce the uniform series or the arithmetic gradient, I think for me at least the idea of these being a conversion kind of helps with kind of understanding what it is. Okay. Okay, and so of course you can flip this formula around too, and so you can take this formula and solve for p, right? And so if we divide both sides by 1 plus I raised to the n, then what we get is p is equal to f divided by 1 plus I to the n. Okay. And so you can manipulate these formulas kind of based on what you need to find. Right? And so as a quick example of this, let's say that you have a situation where you want to have $1,000 in this bank account after 2 years. Okay? And let's say that the bank that you're putting your money in has an annual interest rate of 2%. Okay. And so if you want to have $1,000 in your bank account after 2 years, the interest rate is 2%. You know, the question here is how much money should you put in today? And so it's a little bit of a flip of the previous example, right? And so in the previous example, we were given an amount of money that we have today, right? And we're asked to compute its equivalent amount in the future. Here we flipped it. And so, you know, here this $1,000 that we have in the problem, this is an amount of money that we want to have in the future. And so this $1,000, this is a future sum. Okay. And the 2, well, 2 is both the interest rate and the number of periods, right? But first, you know, 2 without the percentage, we'll call this the number of periods. Okay. And we also have a 2% interest rate. Okay. And so what we want to compute from all these is P. Okay. Because P is the unknown. Okay. And so we're given F, we're given N, we're given I. And so let's go ahead and plug into this formula right here. Okay. And so what we have is 1,000 divided by 1 plus 0.02 raised to the second power. Okay. And so we plug all those numbers in, we punch into a calculator, and what we get is $905.73. Okay. And so with the 2% interest rate, you know, if you are going to leave that money alone for 2 years, okay, with compound interest, then if you start that account with $905.73, then in 2 years you're going to have $1,000. Okay, any questions on this? So this type of calculation here is useful for retirement planning. So, you know, for a lot of people, you know, that have, you know, retirement plans as part of the job compensation, you know, 401ks, pensions, right? A lot of times you're looking to hit a certain number, okay? And so you're hoping to get a certain amount of money in your retirement account by the time you retire. Okay? And so, you know, financial analysts that work at these banks, they say, okay, you know, based on the number that you hope to have in your account by the time you retire at 65, you know, 66, whatever, you know, this is the amount of money that you should be putting away each month. And so they run a very similar calculation to this. Okay. And so far we've covered, I'd say two of the main forms of cash flows. We have, you know, our present sum, which is money that we have right now, and we have future sums, which is a single lump sum of money that you would have in the future. Okay. The next type of cash flow that we're going to be learning is, you know, a bit different in terms of form, but it's very useful for, you know, for a lot of reasons, and that's called the uniform series. Okay. Right. And so what a uniform series represents is that this is a type of cash flow that is consisted of a series of uniform payments. Right. Yep. Okay. And so unlike the present sum and unlike the future sum, this is actually a recurring payment. And so this is one that occurs at multiple instances of time instead of just one. Okay. And so now that we're talking about uniform series, the whole idea of a cash flow diagram is going to become useful. Now this is going to help us visualize, all the different payments for a uniform series. Okay. All right. And it may seem not obvious now. And so, if you've been kind of, looking at the previous equations, we have a letter symbol for each of these different cash flows. And so for present sums, we use P, because P for present. For future sums, we use F for future sum. And for uniform series, we're going to use a letter that doesn't appear in uniform series at all. And so we're going to use A to represent a uniform series. The reason we use A is because most of the times when you're talking about a uniform series payment, especially for an engineering project, these are payments, or these are things that payments or benefits that occur at the end of the year, right? Or at least we assume that it occurs at the end of the year. So if you look back at our cash flow diagram, right? Remember, we always made the assumption that all the payments or all the cash flows occur at the end of the time period. And for a lot of engineering projects, these are kind of planned, in general, kind of on a year-by-year basis, right? And so your cash flow diagram, each of the numbers or each of the tick marks on your cash flow diagram are going to represent years. And so this A here represents, a payment or a benefit that you get annually, right? And so the A stands for annual here for that case. Okay, and so what we're going to do is we're going to compute or derive very quickly, a formula for A that relates it to P and F. Okay. Okay. Because right now we have a formula that relates F and P, and that's our compound interest formula. And so we want to get a similar formula between A and P and A and F. Okay. Okay. And so to do that, let's draw a simple cash flow diagram. So let me draw 3 here. Okay. And if we have a uniform series, what this means is that at the end of every time period, starting at time period 1, we're going to have a uniform payment, right? Okay. And so let's say that this is, in this case, this A here could represent your paycheck, right? And so, your paycheck at the end of every month, we can represent that as a uniform amount A. Okay. Okay. All right, and so what we can do is that even though this A here is a uniform series payment, we can treat each one actually as individual, okay? And in particular, okay, and so if we treat each one as individual, okay, and in particular, let's take those individual amounts and convert them up to the end of the time period, okay? Okay. In other words, what I'm going to do is that, what I'm going to say is that if we look at year one right here, okay, in year one, we receive a benefit of A, right? Right? That's the amount of money that we're getting as shown by the cash flow diagram. Okay. What I want to do is I want to go from year one and I want to transport that up to year three. And so, we want to compute an equivalent amount of money that A is worth in year three. Okay. Okay. All right. And so here, if we look back at our compound interest formula, right? So compound interest, we have F is equal to P times 1 plus I raised to the N, right? Okay. The interest rate we're going to leave, we're going to leave generic because, this type of calculation works for any interest rate. Okay. And so for this particular one, for year one right here, right? Right. And so let's say that, we're sitting on year one, right? And so to us here, that's sitting on year one, that A is a present sum, right? Okay. And so let's call this F1. And so if we take that A and we found its equivalent worth in year three, right? We're going to call that F1. And then now we need to account for how many years are going to elapse between year one, the end of year one, and the end of year three, right? And so if we plug a formula in for that, then we say that, that's going to be 2 years. Okay. Okay. Does everyone understand how we got this formula here for that one? Okay. So I just took the amount of money that we're getting on year one, and I computed its equivalent amount, in year three. Okay. And so we can do the same for the other two cash flows as well. Okay. And so in year two, okay, we're going to use the same formula. Okay, but we're going to call this a different amount. We'll call this F2. Okay. In year two, the fiscal amount that we get is A as well, right? And so P here is going to equal A again. Right? But since from year two, going from year two to year three, we're only going 1 year in the future, we're going to raise this 1 plus I only to the first power. Okay? All right, finally, in year 3, and so in year 3, we're going to compute F3. Okay, and so we look back at the diagram. The amount that we get in year 3 is going to be A as well. Okay. But here, we actually don't need to use our compound interest formula, because to go from year 3 to year 3, well, you just kind of step outside your room. Okay, and so F3 here is just going to be equal to A. And so based on all of these individual F's here, we can compute the total F, right? And so, for this uniform series payment where we get, an amount A at years 1, 2, and 3, we can compute the total future worth of this. Right? And so that's just going to be F1 plus F2 plus F. And so if we plug in the formulas that we have above, we have A, 1 plus I, raised to the second power, plus A, 1 plus I, raised to the first power, plus A. Okay. And this isn't directly related to this example, although, if you remember from last time, I remember I told you that you can't just add up monies together. But in this case, we can just add them up straight up because they're all occurring at the same time period. So, we've already converted all these cash flows to occur at year 3. And so since they're all occurring now at the year 3, we can just add them up. Was there a question? Right, so the N here represents the amount of time in between the two time periods. And so since we're going from year 1 to year 3, only 2 years are passing between year 1 and year 3. Because we go pass over 1, we go from 1 to 2, and then from 2 to 3, which is just 2 years. If we were going from year 0 to year 3, then N would be 3 in that case. Okay, good question. Okay. All right, so this formula, it's not the final formula, and so I'm just going to underline it. That's the formula that we get for this uniform series. All right, any other questions on how we got here? Okay. All right, so of course, a uniform series can be more than just three instances, right? And so we can go ahead and generalize this formula for n periods. Okay. And so instead of stopping at just 2, we can say that the total F here is equal to A 1 plus I raised to the n power plus A 1 plus I n minus 1 plus A 1 plus I n minus 2 ... plus A. Okay. Okay. Infinite series. And so, I will admit that when I was a student, I hated seeing these just because they're hard to visualize. But now that I'm here, I think infinite series are really cool. So yeah. It's not that much longer. We have literally just 3 more lines in this derivation. Okay. So that's good right there. And so that formula right there is a good good formula to have. And so we're going to use that in a second. Question? Oh. Okay, so let's we can do one more thing. And so, even though this formula here is it's truthful, it's a little bit hard to use because, you know, there's so many terms here, right? And so it would be great if we can kind of manipulate this to get rid of most of the terms, okay? Oops. And I kind of spoiled it a little bit because, you know, I marked with the bracket there of all the terms that we actually want to get rid of. Okay, and so the way we're going to get rid of that is we're going to take the same formula here and multiply it by 1 plus I. Okay. And so I'm going to write out the exact same formula, but I'm going to multiply both the left and the right-hand side by 1 plus I. Okay. And so you have F is equal to A. 1 plus I to the N. I'm sorry. So this I kind of messed up a little bit. So this formula here up here should start with N minus 1, right? Because if we look at the formula up here, you know, we're considering 3 years right here, and our exponent here started at 2. Okay. And so that the formula here should start at N minus 2, and these should be, or N minus 1, this should be N minus 2, N minus 3. Okay. So I apologize for that. So that's I was a little bit confused. And so if you want to go back and change your notes, so the previous formula should be F is equal to A times 1 plus I, and it should start at N minus 1, and then it goes down to 1 from there. Okay. And so when we multiply the entire formula here by 1 plus I on the bottom, you know, then we start at N. Okay. I apologize for the confusion. So it's I know when you're talking about the exponents here, it's a little bit messy. Okay. And so by doing that, we actually have 2 equations here, right? And so I've circled them in blue, right? So we have the first equation, that was our original one. That was the one that we kind of read straight off the cash flow diagram that we kind of generalized to N. And we have the second formula there that we obtained just by multiplying the entire thing by 1 plus I, okay? And so to simplify this, we can take these 2 equations here and subtract. And what that's going to do is, because there's so many common terms between the 2 equations, a ton of the terms are going to cancel out, right? And so as an example, right, so let me go ahead and highlight some in purple, okay? And so we have an A times 1 plus I to the N minus 1, A to the 1 plus I to the N minus 1, right? And so since these 2 are matching and we're subtracting these 2, those are going to cancel out, okay? We have the same thing for N minus 2, so that's going to cancel out with that. Okay. And you can't really see it, you know, because there's so many terms more. The N minus 3 is going to cancel out as well. Okay, so a lot of terms here are actually going to cancel out. And what we're left with is just a few different terms. Okay, so this 1 here is going to cancel out on the left as well. Okay. And so what we're left with is Fi is equal to A 1 plus I raised to the M minus A. Okay. And so we kind of canceled out the uniforms, the infinite series of addition by another infinite series of addition. Okay, so fighting fire with fire. And so I'm going to do one thing here just to kind of simplify it a bit. And so I'm going to take this I and divide it by the bottom here, okay? And this will be the first of our formulas that relates F to A, okay? And so what we get is that F is equal to A times 1 plus I raised to the N minus 1 divided by I. And this here is another important formula. And so this is the uniform series compound amount formula. Okay. The names of these formulas aren't that important. And so what I remember this is that this is the F and A formula. It's F and A. Okay. And so we'll go ahead and stop here for today because I did go over time a little bit, so I apologize for that. But are there any final questions on any of this? Okay, all right. And so we'll pick this up on Thursday. And so we'll use this formula. We'll do some examples on this and we'll see how P gets into this as well. And we'll kind of continue this discussion. Okay? Have a great afternoon, guys. Remember, homework is posted. That's due a week from today. If you have any questions on it, just don't be afraid to ask or come to office hours. And I'll see you guys on Thursday.
Thank you, Professor.
Yep.
We do count the attendance?
No,
I know, right? Okay.
I got your email, but yeah, I don't count the attendance, but yeah, it's good for you to come to class.
Yeah. I finished at 1:35.
Okay. Okay. Yeah, I saw you kind of come here. As long as you know, you can come later now, as long as you were quiet, then it doesn't really matter.
Okay, and are you gonna post the lecture notes?
Yes, yeah. So yeah, if you look at the weekly views on Canvas, then the lecture notes are there.
Right.
So I try to put the lecture notes a week before we actually have the lectures.
Okay, sounds good. Thank you.
Yeah.
What was that? Yeah.
Yeah, she just a great one.
No way she did. Was it good? You passed?
Yeah.
Awesome.
Zong, are there, do you have any final questions? Okay, all right, so I'm gonna close the call. And so if you have any questions, just let me know via email.